Usually think of light as something that illuminates, heats, or helps plants grow. But can it push matter in a literal sense? Surprisingly, yes. Under the right conditions, light can exert a real mechanical force, even on electrons inside a material. This leads us to a fascinating and not so well known phenomenon called the photon drag effect. But how can something as intangible as light cause charged particles like electrons to move? Let's start with a simple idea. Light is made of photons, and each photon carries not just energy, but also momentum. When a beam of light hits a surface, that momentum does not just vanish, it must go somewhere. In some materials, particularly metals or semiconductors, photons can transfer part of this momentum to free electrons. The result? A small but measurable electrical current, even though there's no applied voltage. This is not the same as the photovoltaic effect where light excites electrons to higher energy states. In the photon drag effect, it's more like the photons are giving electrons a gentle shove in a particular direction. You might ask, is this effect really observable, or is it just a theoretical curiosity? It's very real. In fact, it has been measured in thin metal films and specially engineered semiconductor structures. For instance, when a beam of infrared light is directed at a gold film at a shallow angle, researchers observe a tiny current flowing in the direction of the light's momentum. That current reverses direction if the light angle changes. The same has been demonstrated in graphene and even in optical fibers, though the signals are weak and require sensitive detection. Why is this effect important, and where does it show up? Photon drag is more than just a physics curiosity. It plays a role in high-speed photodetectors, terahertz devices, and even in understanding radiation pressure in space. In material science, it's used to probe how momentum is transferred at the atomic scale, giving insight into how light interacts with electrons, phonons, and other quasi-particles. It also helps explain why radiation pressure from sunlight can gently push spacecraft equipped with solar sails. Another interesting question, does this work only for conductors? No. While it's most clearly observed in conductive materials with free electrons, variations of the photon drag effect occur in semiconductors and even in dielectrics under specific nonlinear optical conditions. In silicon, for example, intense laser pulses can induce a similar current by shifting electrons through higher-order interactions. Imagine a stream of photons entering a metal like a silent crowd rushing into a hallway. As they bump into electrons, they hand off tiny packets of momentum, nudging the electrons along. The push is minuscule, but with a strong enough light source and a clever setup, we can detect this subtle motion. It reminds us that light is not only a carrier of energy, but also a source of force, capable of stirring motion in the quietest corners of matter. Photons carry momentum despite having no rest mass, and when they are absorbed or scattered by electrons in a conductor, this momentum can be transferred to the charge carriers. The process creates a net drift of electrons in the direction of light propagation, producing a small current without any external voltage. The efficiency of this transfer depends on the photon energy, electron scattering rates, and the material's electronic band structure. In metals, free electrons respond weakly due to rapid collisions, while in semiconductors and two-dimensional materials, the effect can be enhanced by longer carrier lifetimes. The photon drag effect thus provides a direct mechanical coupling between the electromagnetic wave and electronic motion. Irradiating a gallium arsenide wafer with a continuous wave infrared laser induces a photocurrent that reverses direction when the beam direction is flipped. It's like raindrops pushing a boat along a calm lake. Each drop exerts a tiny force, but many drops together produce a measurable drift. The magnitude and sign of the photon drag current vary with the angle of incidence and polarization of the incoming light. Oblique illumination increases the in-plane component of photon momentum, thus enhancing lateral electron drift. Linearly polarized light interacts differently with the electronic states than circularly polarized light, leading to anisotropic drag responses. This angular and polarization sensitivity allows mapping of effective mass and isotropies and scattering mechanisms in the material. Researchers exploit these dependencies to distinguish photon drag from other photoinduced currents. In graphene, rotating the polarization from S to P polarization can invert the direction of the measured drag current under the same incidence angle. It's like adjusting a sailboat's sail angle relative to the wind. Small changes can reverse or maximize the sideways push. Nanostructured metal films support surface plasmons, collective oscillations of electrons that concentrate electromagnetic fields near the surface. Exciting these plasmons at resonance significantly increases local photon momentum density and absorption, thereby amplifying the drag current. Patterned gratings or nanoparticle arrays can be designed to match plasmon resonance to the illumination wavelength. This tailoring results in orders of magnitude stronger photon drag signals compared to flat films. Plasmonic enhancement thus opens pathways for more sensitive, momentum-based photodetectors. A gold film with nanoslit arrays exhibits a 100-fold increase in photon drag current at the plasmon resonance wavelength of 800 m. It's like adding a funnel to catch raindrops. You suddenly channel much more water into a narrow stream. Photon drag depends on the photon energy relative to the electronic band gap and dispersion of the material. In semiconductors, photons with energy near the band edge efficiently transfer momentum to photoexcited carriers, leading to strong spectral peaks in the drag response. Higher energy photons can generate hot electrons that relax before contributing to a coherent drag current, reducing efficiency. The detailed shape of the drag spectrum thus reveals information about band curvature, effective mass, and scattering lifetimes. Spectroscopic studies of photon drag therefore serve as a probe of complex electronic structures. In indium phosphide, the drag conductivity peaks at photon energies just above the direct band gap of 1.35 eV and falls off at higher energies. It's like pushing a swing at just the right frequency. Only certain pushes produce the largest sustained motion. Electron phonon and electron impurity scattering rates determine how long carriers retain the imparted photon momentum before randomizing. Lower temperatures reduce phonon scattering, extending momentum relaxation times and increasing the drag current. Conversely, high impurity concentrations or lattice defects shorten scattering times, damping the effect. Measuring photon drag as a function of temperature thus provides insights into dominant scattering mechanisms and material purity. Optimizing scattering times is key to maximizing the practical utility of photon drag devices. Cooling a silicon photoconductor from room temperature to 77 K increases its photon drag current threefold for the same illumination intensity. It's like sliding on ice versus asphalt. The smoother the surface, fewer scatterers, the further you glide from a single push. Atomically thin materials such as graphene and transition metal dichalcogenides exhibit pronounced photon drag due to their reduced dimensionality and long carrier lifetimes. The confinement of electrons enhances the coupling between photon momentum and electronic motion. Moreover, symmetry objectives in these materials allows unconventional drag effects under circularly polarized light, leading to photocurrent vortices. Such features enable ultra-fast polarization-sensitive photodetection with minimal device thickness. Two-dimensional platforms therefore represent a promising frontier for momentum-based optoelectronics. Graphene devices show photon drag currents exceeding those in bulk semiconductors by an order of magnitude under identical illumination conditions. It's like pushing marbles on a narrow rail rather than a wide table. The motion is more directed and efficient. In many materials, other photodice currents such as photovoltaic or photothermal currents can mask the pure momentum-driven drag signal. Careful experimental design uses angle, polarization, and spectral dependencies to isolate the drag contribution. Time-resolved measurements can separate ultrafast drag currents from slower thermoelectric responses. Patterned electrodes and symmetry analysis further help distinguish between competing mechanisms. Only by ruling out alternative effects can one attribute observed currents unambiguously to photon momentum transfer. By comparing currents under forward and reverse incidence angles, researchers confirmed a sign reversal unique to photon drag, while photovoltaic currents remained unchanged. It's like differentiating wind-driven waves from boat wakes. You analyze wave direction and timing to identify the true source. Photon drag devices offer continuous, bias-free photodetection with polarization and angle sensitivity, useful in imaging and communication systems. Their direct mechanical coupling to light enables detection of optical momentum flux, complementing energy-based photodiodes. Plasmonically enhanced designs allow miniaturized on-chip sensors for integrated photonic circuits. Additionally, momentum detection can measure subtle changes in optical field distributions, advantageous for beam diagnostics. Continued material and structural advances promise practical momentum-sensitive optoelectronic modules. A plasmonic graphene photodetector demonstrated real-time mapping of light's propagation direction with sub-wavelength resolution. It's like a sailboat's telltale lines indicating wind direction and strength, giving immediate feedback without gauges. Exploring photon drag in novel quantum materials and metamaterials could uncover hitherto unknown light-matter momentum interactions. Strong coupling regimes and topological photonic structures may enable giant drag effects or unidirectional currents. Understanding momentum transfer at ultra-fast timescales informs fundamental electrodynamics and quantum optics. Integration with nanomechanical systems might realize light-driven actuators at the nanoscale. As both a probe and a technology, the photon drag effect continues to illuminate the deep connection between light's momentum and electronic dynamics. Theoretical proposals predict that moire superlattices could enhance photon drag by orders of magnitude through flat-band engineering. It's like discovering new gears in a clock. Each gear reveals more about how the entire mechanism truly operates.